Hello everyone. Today we're going to talk a little bit about astronomical scale and distance. As you can imagine, the distances that we measure here on Earth in feet and yards and meters and kilometers and miles, most of those things are not really a good thing to use when we're talking about space because space is so big. So we do still talk a little bit about kilometers, but we're going to learn a couple other measurements that we are going to be using. So let's first talk about scale. Scale is when we represent a relationship between a model of something and real life. So a couple of examples. When you have a map is obviously not real life. It's a smaller version of distances. So you need a scale, and there's an example of that right here. We have a little scale that says this much distance is so many kilometers or so many miles. When you're building a model car or a model plane, we aren't going to build it life size. That would be a 1-to-1 scale. What we are going to be doing is we're building something that's maybe a 1-to-18 scale, which means that every 1 inch on a car would represent 18 inches in real life. There's a video that I made that was the solar system walk, if you haven't seen it. And in that one, our scale was one of my steps matched 6 million kilometers out in space. So the basic unit that we talk about with distance typically in science is a kilometer, meter, or kilometer. So what is a kilometer? A kilometer is 1,000 meters. We walk about somewhere between 3 and 5 kilometers an hour, or 0.0015 kilometers per second. So our moon is the closest major object out in space. We aren't talking about satellites and things, but the moon is the closest bigger one. It's 400,000 kilometers away. So how long would it take to walk there? Well, 400,000 kilometers, if we're walking at 5 kilometers every hour, and there's 365 days a year and 24 hours in a day, we're talking 9 years, a little over 9 years it would take for you to walk to the moon. So driving, now we're going 100 kilometers an hour, that's 4,000 hours. And flying would be 1,000 kilometers an hour, so we're talking 400 hours. So divide that by days. What's that? Roughly 15 to 20 days it would take to fly there in an airplane. So this is just a cool picture of the moon. Our next topic we're going to be discussing are the phases of the moon. If you were paying attention, this last Tuesday we had a full moon. They call it a super moon sometimes because it's a little closer than normal. But we are now moving past a full moon. We're into a waning gibbous. So 1 kilometer is typically not what we're going to be using when we're talking about 400,000 of them and even bigger than that, and that's even to our closest neighbor. For example, the distance to Venus, which is sometimes our closest planet, 38 million kilometers, unless it's on the far side of the sun, and in that case it's 228 million kilometers away. So you could figure out how long it takes to walk that. Divide by 5 and 24 and 365. You can figure out how many years that would take. From the Earth to the Sun is 150 million kilometers. And that seems like a pretty important distance, the Earth to the Sun, since we orbit around the Sun in an ellipse, pretty close to a circle. In fact, old astronomers used to make that kind of a basic unit. And so we call that basic unit, this new unit of distance, we're going to call it the astronomical unit, the AU. So 1 astronomical unit, or 1 AU, is the distance from the Earth to the Sun. And so we can measure other things in the solar system based on that distance. So here's a little picture of our solar system. And you can see on the inside here we have our close planets. We have Mercury, Venus, Earth, Mars, and then we have the asteroid belt. Notice that all those things are pretty close to the Sun in our picture. Then we get to the outer planets. We get to Jupiter, which is the largest planet. Then we get to Saturn. Notice that our spacing between the orbits is getting pretty big. Now we have this humongous leap out to Uranus. Kind of missing the last part of the name there. And then another humongous leap out to Neptune. Watch that solar system walk video if you haven't, and you'll get a sense of how far these distances are. We're talking 9 or 10 steps between the inner planets, and then we're going 100, 250 steps or more as we get to these outer planets. So atomic units are really great when we're talking about things inside the solar system. But once you get outside the solar system, it gets a little bit, that still is kind of not the best unit to use. So inside the solar system, we have Jupiter. We have Neptune, which is 30 atomic units away. Pluto is 50 atomic units away. But now we start getting into these big numbers, right? The edge of our solar system, the Oort cloud, which is on the outside edge of the solar system, now we're at 100,000 units away. Our nearest star, 268,000 atomic units, Alpha Centauri. So pretty soon we're getting into some large numbers again. So enter the light year. Light year is now going to be the thing that we're going to use for most of our measurements outside of our solar system. Light travels faster than anything else in the universe. In fact, it travels 300,000 kilometers per second. You know, we talked about, the moon being 400,000 kilometers away. It can get to the moon and back again in a couple of seconds. So, but that 300,000 kilometers a second, that is constant out in space, in a vacuum. So there isn't anything slowing it down necessarily out there, or it's just so far apart. And this is not just light as far as visible light, but we're talking radio waves and any other kind of electromagnetic wave. So light can travel this constant distance every year of 10 trillion kilometers. And because it's the same distance all the time, we've actually made it a new unit of distance. We call it the light year. So the light year is the basic unit of distance for astronomy versus, say, a meter or kilometer on Earth. Now out in space, we're talking about a light year. This is a picture of our galaxy. If we could take a picture of our galaxy, it would look like this from the top side, the top view. So in the center, we have this massive, supermassive black hole, and all these other things are orbiting around it. This would be approximately where the sun is. Now, we're looking at it from the top down. If you were to rotate it, look at it from the side, it actually is this disk with this kind of, it's pretty thin, but it has this kind of bulge in the center where that massive, supermassive black hole is. So, some distances, since we're talking about light years, our closest star, that Alpha Centauri, that's 4.2 light years away. The thickness of a Milky Way, like I was saying, if you could turn it on its side, we looked at that kind of bulgy part in the middle, that would be 1,000 light years apart. From our sun to the center of our galaxy, to the center of the Milky Way, it's 27,000 light years. So we can look into the center of our Milky Way and we can see where that black hole would be, where all this cluster of energy is. But what we're seeing is energy that has taken 27,000 years to get to us. Our diameter of the galaxy, that's how it is big around, that's 120,000 light years. And our next closest galaxy, which interestingly, we're on a collision course with, but it's not going to happen for a really long time, because it's 2 million light years away. Even if we were hurtling towards each other at the speed of light, we're talking a million years of both of us were traveling at the speed of light towards each other. So it's going to be a ridiculous amount of time before they do collide. Now I did want to say just a little bit about looking up at the sky. The moon, obviously, with it going from full into the waning gibbous and getting smaller, or at least the brightness is getting smaller. That's the obvious thing up in the sky, but you want to be looking at other things. Why else would you be picking astronomy? We need to look at, there's all kinds of cool stuff out there in the sky. So one thing that you might get a little tool for you, especially if you don't have a cell phone or anything around, is a planisphere. Now I do have an optional activity that gives you the ability to print off and cut out this little planisphere. What is a planisphere? It's basically a star chart. It allows you to rotate. There's a little circular pattern in there that you rotate around, and it's got a picture of what the sky would look like when you at that time of year, based on what you rotate it to. Now, I just typically use my phone, and I get an app. The one I typically use is Skyview Lite. There are a couple of Skyview options out there, but there's a whole other list. I did include a website on there that gives you a list of a bunch of star viewing apps. I highly recommend you grab those. The sky has been beautifully clear and it continues to be, so get out there and start looking at stars in the evening. Here's just a general star chart. This is if you're looking to the north. You would see these. You would see Ursa Minor, which is the Little Dipper. We would see the Big Dipper, Ursa Major. If you find the Big Dipper, these two stars here point you towards Polaris. Polaris is considered the North Star. Notice it stays in the north for us, and that's the end of the handle for the Little Dipper here. The other thing that is really interesting over here, if you look out to the west, there's Taurus is here, but just to the right, or just slightly north of that, is going to be Venus. Venus is very low on the horizon, but it is a super bright light in the sky, and you'll definitely see that. One more slide here. The other thing you might look at, I'm pointing to stuff in the west because when I walk out my front door, it faces west, and so I'm always looking at the three stars in the belt of Orion, Betelgeuse up here, Castor and Pollux are both very bright stars in the western sky as well. But you can see a couple of these things. Try and go out, see if you can find these. All right, that's all for this presentation, and enjoy your first week.